All right. Well, hello, everyone. I'm Archit Kulkarni, a software engineer at Anyscale. With me today is Kaishin Chen. Kaishin, you want to introduce yourself?
Hi, I'm Kaishin, and I'm a software engineer at Anyscale and focusing on KubeRay.
Thanks so much for joining us today. We're delighted to talk to you about KubeRay, which is a Kubernetes operator for deploying and managing Ray applications. Today's agenda will cover the core components of KubeRay, including the Ray cluster custom resource, Ray job custom resource, and Ray service custom resource. We'll also dive into some real-world use cases and even walk you through a demo of how KubeRay can handle the whole LLM lifecycle, from fine-tuning to serving and more. Finally, we'll discuss some community news, including collaborations and testimonials. So what exactly is KubeRay? KubeRay is a Kubernetes operator that manages the entire lifecycle of Ray clusters and their associated applications on Kubernetes. To paraphrase the Kubernetes docs, operators are software extensions to Kubernetes that make use of custom resources to manage applications and their components. In this case, Ray clusters, Ray jobs, and Ray services. And I'll talk more about those later. Ray excels at large-scale data computation, especially for machine learning tasks, while KubeRay focuses on seamlessly integrating Ray into the Kubernetes ecosystem. What you can see from this diagram is that Ray provides you with two ways to manage your Ray infrastructure, either directly through the Ray VM cluster launchers or through KubeRay for Kubernetes deployments. In this talk, we're focusing on KubeRay. Why is KubeRay the best solution for running Ray on Kubernetes? Well, KubeRay enables data and ML scientists to focus on what they do best, experiments and computation. Meanwhile, infrastructure engineers can concentrate on the deployment side and on integrating KubeRay with Kubernetes ecosystem tools like Prometheus, Grafana, Nginx, and others. The details of the arrows here are not so important if you're familiar with Kubernetes operators already. It's just a standard pattern for operators. The summary is that both Ray and Kubernetes serve as resource orchestrators, but they focus on different aspects. Ray is all about computation, handling tasks and actors, while Kubernetes is geared towards deployment, managing pods as its scheduling units. So the main takeaway here is that this allows for the separation of responsibilities between data and ML scientists and infrastructure engineers. KubeRay offers three core components for different workloads. For the first use case, imagine you want to have a long-running cluster to submit multiple workloads to, possibly from multiple users. Or perhaps you want to spin up a temporary cluster for debugging, writing unit tests, or prototyping. For these use cases, you can use the Ray cluster custom resource at the top here. The Ray cluster custom resource manages the lifecycle of a Ray cluster. It supports autoscaling, and it also supports GCS fault tolerance for if the Ray head node goes down. And I'll talk more about that later. For the second use case, imagine you have ad hoc workloads where you don't know when they'll be submitted, but you don't want to pay the cost of having a live cluster up and running all the time. For a case like this, you can use the Ray job custom resource. Ray job is essentially two components, a Ray cluster plus a job. It automatically creates a Ray cluster and submits a job when the cluster is ready using the Ray job API. Best of all, you can recycle the Ray cluster automatically after the job completes. Finally, suppose you're responsible for a service, so uptime and latency are prime concerns for you. For this use case, you can use the Ray service custom resource. It not only creates a Ray cluster, but also ensures zero downtime upgrades and high availability, which are features that we'll dive into in the next few slides. To sum it up, you can use the Ray cluster custom resource for both long-running clusters or lightweight ephemeral clusters. You can use the Ray job custom resource for ad hoc or scheduled workloads. And you can use the Ray service custom resource when uptime is paramount. And for those who may be less familiar, a custom resource is simply an extension of the Kubernetes API that can be used alongside the built-in resources that you're familiar with, such as pods, for example. Like other resources, you declare the desired state of the resource, and the KubeRay operator keeps the current state of Kubernetes objects in sync with the declared desired state. And so for each of these three custom resources, we're going to dive into the details of how that's accomplished. We'll start with the Ray cluster custom resource definition. As mentioned earlier, KubeRay follows the classic Kubernetes operator pattern for managing our Ray clusters. This slide shows the architecture of the Ray cluster custom resource definition. As a user, you just need to create a Ray cluster custom resource. The KubeRay operator then automatically takes care of the creation, deletion, and updating of any Kubernetes resources that it needs to spin up the Ray head and worker pods. The idea is to let you focus on the Ray cluster configuration while KubeRay takes care of the Kubernetes aspects. One key feature here is that KubeRay integrates seamlessly with the Ray autoscaler. This allows your Ray clusters to dynamically scale based on the workload. You can add GPU pods when they're needed and remove them when they're not. So here we have a Ray cluster that's going back and forth between these two states where in the minimal state, it's just a head node, which only has a CPU. But if GPUs are needed for a workload, that same cluster can scale up. Using this, you get both performance and cost efficiency. Now let's talk about Ray Job, a custom resource that's particularly beneficial for those concerned about cloud resource costs. You create a Ray job, and then the KubeRay operator springs into action, creating, updating, and deleting the Kubernetes resources. And one great thing about this is, as we mentioned previously, once the job is done, it will automatically delete the Ray cluster, conserving your valuable cloud resources. And the deletion, of course, is an optional feature. You can disable it in case you'd rather leave the cluster up and running for post-mortem debugging. Finally, let's talk about the Ray service custom resource. Before going into the architecture diagram for the Ray service, let's just describe two of the key stability features that Ray service brings to the table. First up is zero downtime cluster changes. Ray service automatically detects both unhealthy cluster states and user config changes that would necessitate a new cluster. In response, it spins up a new Ray cluster, shifts the traffic, and finally deletes the old Ray cluster. And what about high availability and GCS fault tolerance? The GCS, or Global Control Service, is a core component of the Ray head node that manages cluster-level metadata. But even if the Ray head pod goes down, Ray service ensures that user traffic continues to flow to worker pods uninterrupted while the new head pod starts back up. This makes it highly available and fault-tolerant. The architecture diagram for Ray service is pretty similar to the ones we've seen before. The user creates a Ray service custom resource. The operator monitors the service and updates Ray serve applications in place. The KubeRay operator takes care of creating, updating, deleting the Kubernetes resources, just like it does for Ray cluster and Ray job. And note that in the case of the zero downtime feature that I mentioned in the previous slide, the Ray service might be managing two Ray clusters, one of them pending, one of them active, as indicated in the picture. Finally, with the setup, the user, maybe a different user from the one who started the Ray service, can directly query the Ray serve application, which is exposed as a Kubernetes service. In summary, KubeRay is the go-to solution for managing Ray clusters and applications on Kubernetes. It saves time, reduces costs, and enhances stability. So far, we've talked about what KubeRay can do for general Ray clusters and applications. But let's focus on an area that's increasingly important, large language models, or LLMs. Why is this different from traditional ML workloads? There's a transition from CPU to GPU inference. The computational costs increase dramatically. There's also a change in the lifecycle. Instead of starting with data and using it to train a model for specific tasks, companies and startups can take a pre-trained foundational model, which may have been too costly to train themselves from scratch, and then they can fine-tune it for their use case. This shift has resulted in an increasing number of LLM application developers. For LLMs, distributed computation is a must-have. We think KubeRay is uniquely positioned as an optimal solution for deploying and managing LLMs on Kubernetes. We'll share insights on how you can manage all stages of the lifecycle of LLM deployments using KubeRay. And with that said, I'll now hand it over to Kai-Shun to tell you more.
Thanks, Arshad. I'm Kai-Shun. Today I will talk about LLM with KubeRay. The first is that we will compare the difference between the traditional ML model lifecycle and the LLM model lifecycle. For the traditional ML model lifecycle, it consists of several stages, including like data preparation, model training, tuning, and the model serving. And typically, the most expensive part is the model training because it requires a lot of GPU. And for the serving part, maybe it is not that expensive because the model is not large, so you can use single or small GPU for the inference. And as I know, if your workload is not very sensitive to the latency, some companies also use CPU for the inference to save the cost. And our observation is that the performance bottleneck for the model serving for the traditional ML is about the computation, not memory. And then for the LLM model lifecycle, it is a bit different. The main difference is that seldom companies that train their foundation model from scratch because pre-training a large language model is pretty expensive, and it may take several $1 million, and the only big tech can afford it, like the Meta, like OpenAI. Yeah, so based on our observation, most users use open source pre-trained large language models, like Meta's Llama 2, like Falcon, like Vicuna, and then use their dataset for the fine-tuning. Yeah, and the fine-tuning will not cost a lot of money, but for the serving, it's a totally different story because the model becomes very large. For example, like the Llama 270B, in most of industry case, we will not use the quantization, so we will use FP16 for each parameter. So it requires 140 gigabyte of GPU memory. So we need multiple and a large GPU for the inference. So it becomes very memory intensive. So there are a lot of the memory optimization technique, like the continuous batching, like the patch attention from the VLM, like the fetch attention. Yeah, and we have Anyscale published a lot of blogs about that. So if you are interested, you can take a look at it. Yeah, so our point is that the serving becomes much more expensive and important than before. Right, the ML ops industry moved from the training to the serving. Yeah, and for the LLM with KubeRay, KubeRay can manage the end-to-end LLM lifecycle on Kubernetes. And we think that the KubeRay and the Ray are the best solution for large language model on Kubernetes, especially for large language model serving cost. The first is that Arshad introduced that we have the autoscaling because the online serving, the workload is hard to predict. So we require the autoscaling to add or delete our computing resource based on the dynamic load to save the cost. The second is the heterogeneous, because currently it's not it's not that you have money so you can get a GPU. A lot of times that you have money but you cannot get GPU, especially for some high-end GPU like A100 or H100. So support heterogeneous computing resources are very important, like different types of GPU, like TPUs or CPUs. And then we will demo the end-to-end large language model lifecycle with KubeRay. Yeah, this is our architecture of our demo. The first is that we will do the data processing with the Ray cluster, Jupyter Notebook, and the autoscaling. And then after we finish the data processing, we will create a Ray job for the fine-tuning, because the workload, the computing resource requirement for the fine-tuning is able to predict. So we decide to use Ray job to set the course. And then after the fine-tuning, it will upload the model checkpoint to the cloud storage. And then step 3, we can use the Ray service to serve our fine-tuned large language model. And for step 4, we will build an LLM application with the LangChain and the Gradio to showcase the application based on our endpoints served by Ray service. Yeah, for the prototyping side, in this demo, we will not cover this part, but this is a recommendation architecture. The first is that we typically recommend user to run a Jupyter Notebook as a head-pass sidecar container. And then we also recommend user to enable the autoscaler, and the autoscaler will inject a sidecar container into the head pod. And for the second, we will fine-tuning with the Ray job. And in this demo, we fine-tune a Llama 27B on a math data set. And in the demo, we use a Ray chain and a diff speed. And then we have the 16 NVIDIA A10 GPUs and a 24 GB RAM per GPU. And we only fine-tune for one epoch, and it takes 22 minutes. Yeah, and this is our demo video. The first is that we install a KubeRay operator. Yeah, and wait for it to be ready. Right, and then create a Ray job for fine-tuning. Yeah, and check the custom resource. Yeah, and we watch the pod, and it has one head node and 16 GPU worker nodes. And then we monitor the fine-tuning job progress. And then after 20 minutes, right, it succeeds. And you can see the checkpoint here. Yeah, and then because this is for demo purpose, we didn't configure the auto deletion. So at this moment, we did it by ourselves. And then after we finish the fine-tuning, we can serve the fine-tuned model with Ray service and the Ray LLM. And the Ray LLM is a previously named Avery. It is a tool that can help you to serve your large language model on Ray. And it provides the OpenAI compatible API. So it's pretty easy to use the OpenAI Python package to use the endpoint that's served by Ray service. And this is the demo. Wow.
How'd you do it last time? Oh, here we go.
Yeah, we already have an operator that's in our cluster. So we create a Ray service. Yeah, and then we watch our pod. And in the Ray cluster, it will have one head node and one GPU work node. And we will serve the large language model on the GPU node. And then it is ready. So we just try to pull forwarding, and then use a curl request to test it. Yeah, and we got a response. And then the last step is that we have an endpoint that's served by our RAID service with our fine-tuned Llama 27B model. So the last step is that I want to build an LLM application with LangChain and Gradio. And here we use Gradio to build a web UI, and use LangChain to handle the I/O between the RAID service endpoint and our users' input and output. Right? And because this one is our fine-tuned model is fine-tuned with the math data set, so we will use a math question for the demo. And LangChain it will use a prompt template that's as we shown in the slide. Right? This is how we fine-tune our model, so that's why we use this prompt template. Yeah, and this is a math problem that we will use. It is the same from our math data set, and the answer is 5. It's a pretty simple math question. Yeah, and this is the very short video. Yeah, because I have already pull forwarding that to my dev box, so I just run the Gradio server that's on my dev box. And then you can see this UI, and we use the question that's in the last slide, and submit it to our endpoint. Yeah, and the result from our model is not correct, because we just fine-tuned for one epoch. But the response is that it has already followed our dataset format. So it is better than the best model. Yeah, and I'll introduce the current status of the KubeRay, and I talk about the LLM with KubeRay. So currently, I want to recap the 2023 for KubeRay community. From the last RAID summit until today, we have 4 major releases, from 230 commits to more than 600 commits. And we have more than 90 contributors, like Dimitri from Cruise, and Joshing Wilson, and Chen Yu from ByteDance, and Adi from Microsoft, and like Yichen from the UIUC, and several folks from the Red Hat and IBM. Right, we have a very, very good community, and thanks for the contribution. And then we have a lot of users blog, like the Instacart, Samsara, Spotify, and DoorDash, and Google. And we have a massive growth in the number of KubeRay clusters. We have a 9x growth in the last 6 months, and a 2x in the August. And in our expectation, we think that this month we will have another 2x in September. And this is our users' feedback from Niantic, right? Because I am not sure that it is legal for me to use their logo. So I decided to use the Psyduck, which is my favorite Pokemon. Yeah, and Niantic deployed Ray with KubeRay, and they used it for their scan processing, and it saved the cost by 60%, right, which is very fantastic. Right, so we are very happy to announce that KubeRay is generally available. Right, I think you guys know that in the Ian's keynote. Right, and then currently the KubeRay 1.0, the first release candidate, is available. So feel free to try it. This release candidate will be very different from the previous one. For the previous one, we will just iterate with user for release candidate for 1 to 2 weeks. But this one, we will iterate maybe for 6 weeks. So it is a good time if you have any bug, right? It will be fixed very fast. So it's a good time to open some issue. Yeah, and thanks for you guys to attending our talk. Thanks.